Good morning, my dear students. I am Sravani, Assistant Professor in CSE Department, Mlritm College, Hyderabad. Today, I am going to discussing the subject Formal Languages and Automata Theory. This subject is based on mathematical computation. These mathematical computations are used to represent various mathematical models such as finite automata, push-down automata, Turing missions, and also learn the languages, different languages like regular languages, context-free languages, and irregular languages. Okay, now today we are discussing the first concept, Introduction to Finite Automata. In that, these are the concepts we are discussing today. First one is finite automata. Second one is model of finite automata. Third one is central concepts of finite automata. Fourth one is representation of finite automata. Representation is also called as structural representation of finite automata. Next, types of finite automata. So here basically two types. First one is DFA and second one is NFA. So these are the topics today we are discussing the introduction to finite automata. So first one is before introducing introduction to finite automata, first of all, what is meant by automata? So the term automata is derived the Greek word. So the term automata means self-acting. Self-acting is nothing but it performs sequence of operations automatically. That means we are consider traffic lights, elevator system, like that. We are consider any these two examples. Okay. Next, the automation is also known as abstract mission. Abstract mission is also called as just it is a mission. So it performs computation of input by moving through a series of states. State is represent nothing but state represents circle. Okay. So next, what is finite automata? Finite automata is nothing but collection of states is called as finite automata. Finite automata is also called as finite state mission. It is used to represent 5 tuples. First one is Q, sigma, delta, Q naught, F. It is used to represent how many tuples? 5 tuples. First one is Q, sigma, delta, Q naught, F. Where Q indicates finite set of states. State can be represented as circle. State can be represented as circle. Next, sigma. Sigma indicates finite set of input symbols. Sigma indicates finite set of input symbols. Next, delta. Delta indicates mapping function or transition function. Mapping function is also called as transition function. Next, Q naught indicates initial state or final state. Initial state is also called as final state. F indicates finite set of final state. Any finite automata contains only one initial state, but it contains any number of final state. Let us consider one example. So this is my finite automata. Here Q0, Q1, Q2 are states. Input symbols are 0, 1. Okay. So Q indicates, in previous slide we are discussing how many tuples? 5 tuples. Q, sigma, delta, Q naught and F. In this example, Q represent finite set of states. Finite set of states. So here states are Q naught, Q1, Q2. States are Q naught, Q1, Q2. Next, sigma. Sigma indicates finite set of input symbols. Here input symbols are 0, 1. Input symbols are 0, 1. Next, delta indicates transition functions or mapping function. Let us consider delta of Q naught of 0. delta of Q naught of 0, it goes to Q naught only. So, it goes to Q naught. Next, delta of Q naught of 1, Q naught of 1. So, Q naught of 1, it moves to which state? Q1 state. Next, delta of Q1 of 0, Q1 of 0 equal to Q1 of 0, it moves Q1 and also Q2. Q1 and also Q2. So, Q1 of 0, it moves to Q1 comma Q2. Next, delta of Q1 of 1, it moves to Q2 only. Next, delta of Q2 of 0, delta of Q2 of 0, it moves to Q1. So, this is the sample example to represent 5 tuples. Let us consider another example. Let us consider Q0, Q1, Q2. So, initial state is Q0, final state is Q2. Initial states can be represented single arrow. The final state represent double circle. Okay. So, inputs are A, B. So, in this example, Q indicates number of states. In this example, number of states are Q0, Q1, Q2. Sigma equal to input symbol, set of input symbols. Set of input symbols are either A, B. So, next, mapping function. Mapping function is Q0 of A, it moves to Q1. Next, Q0 of B. Q0 of A, it moves to Q0 only. Next, Q0 of B, it moves to Q1. Next, Q1 of A, it moves to Q1 only. Q1 of B, it moves to Q2. Q2 of A, it moves to Q2. Q2 of B, it moves to Q2. Okay. Next, Q0 indicates initial state. Here initial state is Q0. Final state is Q2. Final state can be represented as double circle. So, simply finite automata can be represented as 5 tuples Q, sigma, delta, Q0 and F. Okay. Next. So, in this example, the circle represents states. So, this circle represents states. Next, the arc labeled with input alphabet shows the transition. That means this label shows transition function or mapping function. Next one is the initial state is denoted by empty single incoming arrow. So, this single incoming arrow is called as initial state. Next, final state is indicating double circle. So, here final state representing double circle. So, this is the finite automata. Next, model of finite automata. Model of finite automata consists of mainly 3 parts. First one is input tape. First one is input tape. Second one is read-write header. Second one is read-write header. Third one is finite control. Third one is finite control. Model of finite automata is also called as structure of finite automata. So, here mainly contains how many components? 3 components. First one is input tape. Second one is read-write header. Third one is finite control. So, first one is finite automata can be represented by input tape, finite control and also read-write header, and also it contains read-write header. Read-write header. First one is input tape. So, here input tape is divided into number of cells. Each and every cell is associated with one input symbol like A, B, 0, 1, 2, 3 like that. 0, 1, 2 like that. Okay. Next, finite state. The finite control decides the next state on receiving partial input from the input tape. So, here input tape reader or write header read write control is used to read input from left to right. At a time read only one character. So here finite control is also contains state information. For example, Q0, Q1, Q0, Q1, Q2 and so on Qn. For example, Q0 of A. For example, input symbol contains, input tape contains number of cells, right? Each and every cell is associated with one input. For example, A, B, like that. For example, Q0 of A, it goes to same state or another different state. For example, Q0 of A, it goes to next state. For example, that means it is Q1. Next, read write header, read next character in the input tape. Next character means here next character is B. So next Q1 of B, it goes to same state or next state. This is the mathematical model of finite automata or structure of finite automata. So mathematical model contains how many components? Input tape, read write header and finite control. So next one is central concepts of finite automata. In this, we are discussing what is symbol, what is alphabet, what is string, what is language. So these all are interlinked concepts. First, what is meant by symbol? Symbol is an entity or one character is called as symbol. Symbol is nothing but one entity or one character or individual objects which can be any letter, digit or any special character. For example, let us consider A. A is one symbol, right? Let us consider another C. C is one symbol. Let us consider 0. 0 is one symbol. Let us consider 9. 9 is one symbol. Next, any special characters. For example, dollar. Dollar is one symbol. Symbol is nothing but any one character. Character is nothing but a symbol. Next, alphabet. Next one is alphabet. Alphabet is nothing but collection of symbols is called as alphabet. Collection of symbols is called alphabet. For example, in previous, A is one symbol, B is one symbol, C is one symbol. Here, alphabet is nothing but collection of symbols. For example, AB, BA, AA, BB, like that. These collection of symbols are called as alphabets. And also in represent 0, 1, 1, 0, 0, 0, 0, 1, 0, like that. Okay. So, what is meant by alphabet? Collection of symbols are called as alphabet. Next, string. Collection of all alphabets is called as string. Finite sequence of symbols of sigma or simply called as collection of alphabets are called as symbols. Let us consider one example. A, B are two symbols. So, strings A, B, AA, BB, ABB, AAA, like that. Okay. Infinite of strings can be generated by, so let sigma 0, 1 can be an alphabet. So 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 0. Okay, like that. Simply string is nothing but collection of alphabets is called as string. Next, what is meant by language? Collection of appropriate strings are called as language. Here we are observing one word, appropriate language, appropriate string, collection of appropriate. It is not a collection of strings, it is a collection of appropriate string. That means, let us consider one example. So, to design finite automata that contains substring 0, 1. Substring 0, 1. So, strings are first 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, like that. Okay. So, appropriate collection of strings are called as language. Let us consider set of language over the starting with 0. Starting with 0. That means any string starting with which symbol? 0. So first one is 0, starting with 0. Next one is 0, 0. So starting with here 0. Next one is 0, 1, 0. 0, 1, 0 starts with which alphabet? 0. Next one is 0, 1, 1. So here also string starts with 0. Next 0, 1, 1. Here also string starts with 0. Next 0, 1, 0, 1. Here also string starts with 0. Let us consider another example. String starting with 0, 1. So let us consider sigma equal to first string is 0, 1. Next one is 0, 1, 0. Next one 0, 1, 1. Next one is 0, 1, 0, 1. Next one is 0, 1, 0, 0, like that. So what is meant by language? Collection of appropriate strings are called as language. Okay. These are the central concepts of finite automata. Symbol is nothing but collection of simply an entity or character like A, B, 0, 1, like that. Okay. Next, alphabet. Collection of symbols are called as alphabet. Next, string. Collection of alphabets are called strings. Collection of appropriate strings are called languages. Okay. Next concept is structural representation. There are two ways to represent finite automata. First one is transition diagram, is also called as state diagram. It is also called as state diagram. State diagram. Next one is transition table. So transition diagram consists of states, input symbols, mapping functions, initial state and final state. Let us consider one example. So here state represent circle. State represent circle. Next, transition means one arrow, single arrow. Transition from one state to another state represent this representation. Next, starting state. This is the starting state. Next, final state. Final state can be represented as double circle. Final state can be represented as double circle. These are the notations in transition diagram. So, this is my example transition diagram. Okay, here Q0 is initial state. Q2 is final state. Q2 is my final state. Q0 of 0 is transition function. Q0 of 0, it moves to Q0 only. Next, Q0 of 1, it moves to Q1. Next, Q1 of 0, it moves to Q1 only. Next, Q1 of 0, it also moves to Q2. That means Q1 of 0, it moves to Q1 and Q2. Next, Q1 of 1, it moves to Q2. Next, Q2 of 0, it moves to Q1. This is transition diagram. Transition diagram contains states, initial states, transition function, final state and mapping functions. Next, transition table. So, there are two representations now. So, first one is transition diagram. Second one is transition table. Transition table is also called as tabular representation. So, it takes two arguments, a state and a symbol, and returns a state. That means next state. Transition table represents the following things. First one is column. Second one is rows. Column corresponding to input symbol, rows corresponding to states. So here column represents, so in previous, column represent input symbols. So column represent input symbols. Next, rows corresponding to states. So rows corresponding to states, like that. Okay, so here by using this transition diagram, I follow or draw transition table. So states are Q0, Q1, Q2. So initial state is Q0, final state is Q2. Input alphabets are here 0, 1. So Q0 of 0. So Q0 of 0, it goes to Q0 only. Next, Q0 of 1, it goes to Q1. Next, Q1 of 0, it moves to Q0. It moves to Q1 and also it moves to Q2. So Q1 comma Q2. Next, Q1 of 1, it moves to Q2. Next, Q2 of 0, it moves to Q1. Q2 of 1, so nothing. So null string. Okay, so this is transition table. There are two ways to represent structural representation of finite automata. First one is transition diagram, second one is transition table. Next, types of finite automata. There are basically two types. First one is finite automata with output. Second one is finite automata without output. Finite automata with output again divided into two types. First one is Murray mission, second one is Mealy mission. So, finite automata without output contains three. First one is NFA, first one is DFA, second one is NFA, third one is NFA with epsilon. Basically two types. First one is DFA and second one is NFA. NFA contains two types, NFA without epsilon and NFA with epsilon. So basically two types, finite automata with output, without output. With output, two types, Murray mission and Mealy mission. Without output, three types, DFA, NFA and NFA with epsilon. Okay, so basically there are two types. So first one is DFA, second one is NFA. DFA stands for deterministic finite automata. DFA stands for deterministic finite automata. NFA stands for non-deterministic finite automata. Coming to DFA, DFA stands for deterministic finite automata. It is one type of finite automata. It is also represented as 5 tuples. It is also represented as 5 tuples where Q, sigma, delta, Q naught, F. So, where Q indicates finite set of states. Q indicates finite set of states. Sigma indicates finite set of input symbols. Sigma indicates finite set of input symbols. Delta indicates transition functions or mapping function. So, Q naught indicates initial state or final state. Q naught indicates initial state or final state. Simply, Q naught belongs to Q. That means Q consists of set of states. So, Q naught belongs to which states? Q state only. F indicate set of final states. Okay. This is the graphical representation of finite DFA, finite deterministic finite automata. So, vertices represents the state. The arc represents with input alphabet shows the transition function. Initial represents the empty single incoming arrow. Final state indicates double circle. So, this is sample representation of DFA. So here initial state is Q naught. Final state is also Q naught. Sigma input symbols are 0, 1. States are Q naught, Q1. Mapping functions of Q naught of 0. Q naught of 0, it moves to Q1. Q naught of 1. Q naught of 1. Q naught of 1, it moves to Q naught only. Next, Q1 of 0. So, Q1 of 0, it moves to Q naught. Next, Q1 of 1. Q1 of 1, it moves to Q1 only. This is the sample representation of DFA. Next, NFA. NFA stands for non-deterministic finite automata. So here also represented as 5 tuples: Q, sigma, delta, Q naught and F. Here where Q indicates finite set of states, sigma indicates finite set of input symbols, delta indicates transition functions or mapping functions, Q naught indicates initial state, F indicate finite set of input symbols. So any finite automata, it contains only single initial state but indicates number of final states. So here, what is the difference between NFA and DFA? Both are represented as 5 tuples. So the main difference is transition function. In DFA, Q into sigma tends to Q only. In previous slide, observe this one. So, Q into sigma tends to Q. That means one input symbol, it goes to only one next state. Okay? It moves only one transition. It contains only one transition. But in case of NFA, it contains multiple transition. That means Q into sigma tends to 2Q. Here Q, that means only one transition. In NDFA, NDFA is nothing but both are same. NFA and NDFA are both are same. Non-deterministic finite automata contains multiple transitions. Both are 5 tuple representations, right? So what are the differences between graphical representation of non-deterministic finite automata? So here A, B are states. So input alphabets are 0, 1. Initial state is A. So let us consider final state empty. That means we are consider, for example, C. C is my final states. Okay. Initial state is A. Initial state is A. Final state is C. Final state can be represented as double circle, right? Mapping function. Q A comma 0. A comma 0 is A of 0, it goes to 0. A of 0, it goes to A and it goes to B. That means A comma B. Okay, right? Next, delta of A comma 1. A comma 1. A comma 1, it moves to B. B only. Next, B. B of 0. B of 0, it moves to C. It moves to C. Next, delta of B of 1. B of 1, it moves to C. Okay. Next, C of delta of C of 0. C of 0, it moves to B and it moves to 0 C only. That means B comma C. Next, delta of C of 1. That means it moves to C only. So observe this case. So in NDFA, it contains multiple transitions. That means here A of 0, it moves to A and it moves to B. That means here 2 transitions, right? One input symbol contains how many transitions? 2 transitions. Let us observe in DFA. So here Q naught of 0, it moves to Q1. Q naught of 1, it moves to 1. That means in DFA, it contains only one transition. So differences between DFA and NFA. So in previously we are discussing, right? So single particular next states for each input symbol is called as deterministic automata. That means simply one next state, one input having one next state. Here multiple next states. In NDFA, first one is multiple transitions are called NDFA. In DFA, it does not allow epsilon transition. That means empty strings. It does not allow epsilon transition. But in NDFA, it allows epsilon transitions. Epsilon means in NFA contains how many types? NFA with epsilon, NFA without epsilon, right? So in NDFA, it allows epsilon productions. In DFA, does not allow epsilon productions. Next, in DFA, it allows backtracking, but in NDFA, it does not allow backtracking method. So, in DFA, it requires less memory, but in NDFA, it requires less memory. Sorry, in DFA, it requires more memory, but in case of in NDFA, it requires less memory. It requires less memory. So in DFA, the final string is accepted by DFA. It is transformed to or moving to final state. That only string is accepted. Otherwise, rejected. So in NDFA, the string is accepted by NDFA if at least one of all possible transitions ends in a final state. So these are the differences between DFA and NFA. Okay. Thank you.